Okay, so we were here after discussing the effect of solvent contribution, the hydrogen bonding interactions, and how it affects the NMR. And besides water and other solvents which can contribute through hydrogen bonding, there is also some interactions such as the aromatic rings. These were the things that were discussed last time. One common thing that we found that whenever you have hydrogen bonding, there is broadening of the NMR peak, and so we saw there is also shift to the uh, higher chemical shift values. And when you have aromatic ring like a solvent such as benzene, if you take benzene as a solvent, then it depends if the solute lies in the plane, solute nucleus lies in the plane uh, of the ring, then it is having a de-shielding effect. And if it is lying here as shown in the picture, then it will be a shielding effect over here. Okay, so that will lead to cancellation of the applied magnetic field, and that means you will have to apply a greater magnetic field to make it come into resonance with the fixed source of radio frequency. Then this is the next part that we started but couldn't discuss much on this. So this is the because we had already discussed this uh, the intensity aspect of this simple ethanol spectrum, NMR spectrum of ethanol, but I kept it for later part. The thing that splitting pattern, the explanation of splitting pattern was kept for the later part. Yes, and it was this that we were trying to understand the splitting of resonance lines, NMR lines in methanol. So we had you clearly saw earlier that CH3 protons, triplet, and CH2, the methylene proton, they are showing a form which is quartet, four lines. It is split into four lines. So why and how this happens, it is this is what we had to understand and develop a pattern so that you can predict what kind of splitting can happen, what kind of pattern you will get. So this is something that we were trying to understand when we last had class. We were having our last class before this your presentation started. Okay, so there is something that that happens, that you have two nuclei, and uh, so there is a magnetic nucleus which can create a local field which is experienced by the other, and what we know as the interaction of the two uh, vectors, that magnetic moment vector. So that is a coupling constant J that is defined as the interaction strength to represent the interaction strength of the two nuclei, which may be so such that the energy of interaction is given by the dot product, and that's why we call it scalar coupling constant. So it is the dot product of the two interacting spins, and the proportionality constant here, when you remove this, it is equal to hj by h cross square. And that also you can correlate to that, why it is this expression is coming, why this constant of proportionality is having such value, because each of the angular momentum is proportional to h cross. So it's not difficult to find. uh, so this is the spin coupling constant is inherent to two nuclei. It is not dependent on the magnetic field, applied field. It is independent of the applied field, and Yeah, so it can be given by so if that you have a system, say uh, two nuclei having two distinct chemical shift positions, and one of them splits the by certain amount. The second, position at the position of second nucleus also in the NMR spectrum, you will find same splitting pattern. If it is 1:1 interaction, then second nucleus is also split by this for the by the same extent. So the separation between the two lines would be same. So we'll just see by example. So let's take an example. So the starting point was that we take it like the letters in alphabet. So suppose if two interacting spins in nuclear spins are having very different chemical shift values, such as, then we name it the interaction of A and X type interactions, because to represent that in the similar way, in an alphabet A and X are well separated, but if you talk about A and B, they are the neighbors. So to distinguish in the same the interaction of these two kinds, we label them as, we denote them in terms of A and X if they are well separated in terms of chemical shift values, and if they occur close together, they are labeled as A and B if their chemical shift values are very similar. So first we are going to discuss the A and X type interaction. So two nuclei X system, where assuming that both of them are spin half nuclei. mm, of course the two chemical shift values mean that they come into resonance at different frequencies. They have different Larmor precessional frequencies, and yeah. So so this was for the single system that we considered. If we had one nucleus which was and the field applied, this was the separation that we obtained. Okay, field on. Now we are talking about interaction between two spins, so we have to consider them together, and you will have you can find four combinations for two interacting spins, nuclear spins, two nuclei which are interacting. So you can have alpha alpha, that is plus half, alpha A B X. So the X at the X nucleus is having minus half spin, whereas A is having plus half, and so on. So beta represents, so you know, alpha and beta. Alpha is for uh, to denote, alpha means you are talking about ms value being plus half. So this is the wave function corresponding to this, whereas spin wave function. So alpha is the, just as you write psi for electronic wave function, alpha and beta are written for spin wave function, right? So when you write alpha, that is the expression for ms being plus half, and if you write beta, that is a wave function to represent the wave function which is having ms, the spin, as um, magnetic spin this value as minus half. So you can have possible four combinations. So alpha A atom can have plus half or minus half, and so the same alpha A if you keep that spin same, the X can change from alpha to beta. Then you can change the two different, keeping the A same, you can change the X uh, nucleus from plus half and minus half. You can clearly see that. um, so if you are, so beta fix, alpha is plus half, alpha x is plus half, and x is minus half spin, the quantum number. So this is how you have four possibilities are there. Four spin states are possible. And if in absence of any spin-spin coupling, they just appear like this. No spin-spin coupling, these are the four states that we can imagine, and accordingly you can assign the h mu a, Larmor frequency of a, Larmor frequency of x. So when both are alpha alpha, you have minus lowest possible spin, that is both are aligned with the magnetic field. As I told you, the magnetic moment will be aligned in that case. So that is very initial thing that I told you about electron spin and the direction of magnetic moments. So so this is what happens in absence of any spin-spin coupling. The moment they interact, there will be additional contribution due to the interaction, the J coupling constant, and you can see. So when both are having alpha alpha, that is minus half. So sorry, this is the ms is equal to plus half for both. Ms is equal to plus half for both. Or here, when both have ms minus half, in these cases the energy is raised by 1 by 4 hj. You can see this happening. So this is the level that now you have. And in all other cases where both states alpha and beta states are mixed, there due to the coupling, this interaction is lowering down the energies. So in totality you will have four such interactions are possible, which initially, if in isolated conditions A was having one transition possible, now the possibilities are more. So you can see when the place of there are two transitions which correspond to alpha. Look at this, alpha A to beta A, right? Alpha A to beta A, keeping the other part constant. So both, so we are talking about this arrow and this arrow, okay, and both of them differ by this much amount. Sorry, so थोड़ा सा बड़ा खींच दिया, this factor, only this much amount, right? So this is what is the representative of the separation between the two lines that you will have on the spectrum. So in the same way you can think of the two transitions. When the x changes its value from alpha to beta, x change in the value of x, wave function of x, transforming from upspin to downspin, plus half to minus half. So there you can see you have one is here, another one is this one, this particular thing. So again the difference is the same between the two transitions. So this is one line, this arrow represents one line, this is another, and the separation between the two corresponds to this. So at the position of A, you will find two lines now, of one with a slightly higher energy, one with a slightly lower energy, and this will be given by sorry, where is that? So this you will find, you can actually, if you substitute the values, the interactions, it is not very difficult, because we have already seen the expression for energy when spinning nuclei is put in magnetic field. So we are also aware of the sigma, the shielding constant, how it de, um, the the field secondary field that is created by the circulating electron around the nucleus. So that is 1 minus sigma. This expression we have already learned. So the expression for A, the similar expression for x we can write, and this the magnetic quantum number for the spin, for the nuclear spin, ma, mx, are the two different uh, positions in the chemical shift spectrum you can have. So MAMX. So this simplifies to writing is in this way: energy of interaction with the Larmor mu A and mu X being the Larmor frequencies of the A and X, and MAMX they are quantum numbers that which can be plus half or minus half, like that, alpha or beta. So this is the expression that we so 4 lines that we obtained in previous slide, that was corresponding to that. And the expression for when the coupling up happens, this is the term, the J term, which appears. In absence of any coupling, this is the energy. So in absence of any coupling, this is the expression. And now when the spin coupling constant is coupling is taken into account, the energy is changed by this much amount. So now if you substitute the values one by one of A and X, MA and MX, which can be plus half or minus half, you will automatically get that kind of diagram we made shown in the previous picture. So if J is positive, so if J is positive, then when you write MA into MX, that will be MA MX is going to be negative if alpha and beta, if one is alpha and another is beta, then this whole term will become negative. And so you find that so this is the reason why when we have beta alpha or alpha beta, this term is negative and the energy is lowered. But in the case if you have MA, the interaction strength J is positive, and you are having alpha alpha or position, then your MAMX, in this case multiplication term will be plus half into plus half, which will be 1 by 4, right? Or when we are talking about beta 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 beta, in this case also you will have minus half and multiplied with minus half, and this will be again 1 by 4 Hj. So that's how 1 by 4 Hj is coming, reduction by that much amount we are obtaining in each of these cases. We are having a positive sign, so plus plus, so minus minus is also plus, plus plus is also minus. So in these two cases you are seeing an increase by 1 by 4 Hj, 1 by 4 Hj in both cases. If you are having alpha alpha state or beta beta state of spins, then in these two cases there will be increase in energy by 1 by 4 Hj. And if you have any other condition, alpha or beta, for any of the two nuclei X or A, you will have the reduction as we have shown by this much amount. Okay, so this is the thing that we can find. Okay, so so this is the case when J is positive, and the second condition is if J is negative, interaction strength, the coupling constant is negative. In that case the reverse will happen. mm, so sorry, if J is negative, yeah, so you can have again so let's stick to the first condition and analyze the situations for many of the examples. We'll come back to the second J is negative term, and we'll see that Okay, so we see that alpha alpha states, beta beta states, both are raised by 1 by 4j, and alpha beta, beta alpha both are lowered by 1 by 4j. So this is what we have seen, and this is another way of representing the same diagram. So you can, starting from alpha a x, alpha a alpha x, you can have either a change in the x nucleus spin or a. So you see, keep one of them constant, so alpha x is constant here, alpha x, and there is change in the a alpha, so the spin state of the a nucleus changes like this. So the dotted line, the two dotted line that you see, they represent change in the value of b x nucleus, and they will have same separation as the difference between the two solid lines that has been shown already. Okay, so the same it is a different way of expressing the uh, thing which was presented on the previous slide. So there are two transitions that we have just seen, alpha 8 corresponding to alpha to beta for the a spin, for the spin of a nucleus, when the ax is alpha x, and there is another transition. We can see that alpha same for the a nucleus, alpha to beta transition will occur when the x is beta x is having a beta spin. So these are the things that we have just considered in the previous slide. So if you are looking at the lines that we see, they will be separated by h mu, so plus half, they will be located at h mu a plus half j or h mu a minus half j. So the separation between the two lines will be equal to j plus half j minus half j. So the separation, so this is, so one line appears at h mu a plus half j, and the other at h mu a minus half j. So the other one is at minus half j. So the difference between the two, difference, if you calculate, this will be equal to j hj. So it will come out to be j, sorry, uh, half, so half hj units, it will be something like this. Yeah, half hj. So h is a constant, so there's, so the separation between this scale, in the scale, would be in terms of, can be represented in this way by j. So this is the h mu uh, a minus half hj, and this one is for h mu a plus half hj, and the distance, the separation between the two is this. Similarly, the two at the position of x, instead of yeah, you will again have two lines which are separated by, in a similar fashion, separated by j. So the splitting, so when we have two interacting nucleus a and x, the spins, due to a spin coupling, we can have both split into doublet, that and each having the separation j at the two positions. So this is the, so at the given chemical shift value of a, which initially isolated condition, you will have single line, now it is split into this and this. Similarly, if in absence of a, it would have been a single line over here, now it is split into two, right? This is what we are having, experiencing in the NMR spectrum. So now yeah, so this is what I told you. Similar thing will happen with so A position, X position, both of them will have separation by the same amount in this manner, and so both will appear as doublet. So if now think of, so we have seen the same splitting pattern, so now we can also think of species. If suppose you have a system where you increase the number of X type nucleus is increased, AX2, AX3, what will happen? What will happen to the X? What will happen to A? The signal of A, NMR signal, how it will behave. So in AX2, what will happen? Their X resonances will, because there are two of X types, so the intensity will be at the same position, but only the position will of chemical shift is same, but only the intensity is high. So intensity is increased. Rest of the things will remain same for the X. For the X nucleus, uh, there won't be any change in the positions of the chemical shift. There won't be any change in the splitting pattern. Splitting it will be still remain a doublet, but the intensity will be doubled in AX2 as compared to AX, because there are two such nuclei which are giving rise to that signal, NMR signal. So we have intensity increase, a group of so these are equivalent nucleus, so they resonate, uh, they show NMR signals like there is a single nucleus uh, uh, of the same time. So these are the equivalent nuclei X. So number of X nucleus has increased, and so X we are talking about. If we are talking about proton, it is a proton nucleus, but which appears at a very far away positions in the chemical shift values. So such nuclei, if it is increased, the interaction will for the X, the outcome is that for the X nucleus, whether you have AX, AX2, AX3, there will be a doublet due to the interaction with A, the spin-spin coupling with A, and the increase in intensity would be observed as you go from AX, AX2, AX3, nothing more than that. Now, what will happen to the A resonance? We have not yet considered, we have talked about the X. What will happen to A, the resonance of A, when in the AXN type system? This is the point that we are going to, this will be different from what we have just discussed. AX2 system is clear. There was only one A which was affecting all these equivalent nucleus of X type, uh, all the nuclei of X type. And now what will happen in case of A signal? One A, the interaction, the coupling, spin-spin coupling by one X splits into two, so that is a doublet you will obtain. So one X, now first X, this is the A signal, and due to interaction with first X, you are having, it is splitting into two. Now this interaction with the second X, it will be split again into two. So this is the interaction with second X. So interaction with first X. So A is having interaction with the X number 1, X number 2, and each one of them is going to split it further. So the result will be the same amount interaction, because the coupling constant is same as J. Nature of nucleus is same. A, and so the number of nucleus of X type has increased, AX1 to AX2. So the resultant is that you have two of them are strengthening in the middle. So here it is the double, so intensity will be 2, here intensity will be 1, 2. So you see, because of this you are getting the different things. Okay, so this is 1 is to 2 is to 1. So you are obtaining this kind of signal for A. For the X, as I told you, there was only increase in intensity. For the uh, signal of NMR signal of A in AXN system, it gets split as the number of X increases. Okay, so this is the scheme that you can build if you start increasing the number of X nuclei. You can go on extending this thing in the same manner. So the splitting, so the resultant in this case AX2 system is that we are getting, so interaction of both the spin half nuclei, one appearing at extreme of a chemical shift value, other extreme of chemical shift scale. This is the pattern that will obtain for if you are looking at the A signal. So the signal NMR signal for A will be split into a triplet. Final outcome will be that it is, so and this triplet appearance that we are getting, we understand now that it is the first X which interacts and splits into two. Then each of these two signals are further split into two more signals, and two of them are at the same position in the chemical shift value. So we have, they add up, and you get an increased signal in the middle, giving you 1 is to 2 is to 1. So triplet of this kind, yeah, this is the signal that will be obtained, and in this way you can go on building. So x1, x2, second x3, and so on. So you can go on making this kind of triangles, which is so what is you find special about this triangle, you see, 1, so equal intensity 1 1, and the second we are writing a sum of the two, 1 plus 1. Okay, then look at the next panel, we are writing 2 plus 1 3, 2 plus 1 3. So this is a scheme that you can build up very easily, or you can look at this, you can understand from here also. 2, now each one of them in the third interaction, each of these lines will split further into two equally spaced lines. So three of them are strengthening each other, so like this. Or so the same thing is in numbers, we can, so what we are showing in pictures here by the interaction of a x n. So first x, second x, third x, and so this is the pattern that follows the same. So you can easily find that each so first one with the interaction of first x, it splits into two, then each of these two signals that has been split will split into two more such signals having the same j separations in amongst them. So two indices, so in this manner again you carry on this scheme further, so you will have three of them appearing at one position. So 1 is to 3 is to 3 is to 1. So this is the interaction in AX3. And if you are writing in, so the same thing can also be, as I told you, can be expressed by this kind of triangle which we can make. So in this triangle, every, so in the so you start from the top, and go on pattern. So for the equal splitting, first you write this for interaction with first x, then second x, third x. So see, it is split into equal things, and after that you see a pattern. What is the pattern? You see every number that you are writing in the third panel next row is a sum of the two which we have already written. Okay, so 1 plus 1 2, and then you are 1 1 at the other extreme you are writing. In a similar fashion, 2 plus 1 is 3, which we are writing here. 2 plus 1 is 3. So you can see here 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4. So this is how your triangle builds up. You can see the pattern, right? So as you go on increasing the number of x in AXN type of interactive system, this is how you are going. 4 plus 1 is 5, 4 plus 6 is 10, 6 plus 4 10, 5 plus 4 plus 1 5. So this is a pattern which you can easily make by making this kind of triangle, which is called the name given to this kind of special triangle that we are making is called Pascal's triangle. Every entry is the sum of the two entries immediately above it. So I have already shown this pattern, discussed it. Okay, and if you draw this kind of pattern, you can very well predict the splitting that is going to happen in an for the A resonances in AXN type system. A NMR signal of, so we are talking about NMR signal of A in AXN. Okay, so this is how it will change. And so this is so that was this coupling of nuclei which were having half spin. What we can further have, that will be in the next slide. Okay, so this is the pattern we have just for protons, which is half spin half nucleus. So we have already talked about Pascal's triangle. So AX4 we have so this is AX4 system. So X1, X2, X3, X4. So 4X. If you have, then you can see 1 is to 4. So there will be 4 lines appearing. 1, sorry, 1, 2. When you have 4x, AX4 type system. So we are talking about AX4. The 5, 1, 2, 3, 4, 5. 5 lines appear, and 5 is called what you quintet. 4 lines appear when you have x is equal to 3. For AX3 type system, you are having, what will this be called? So this is, so you can say, so this is a quadruplet, so, sorry, quartet कहते हैं इसको, triplet here, doublet, okay, like this. So the so now this is a pattern for, suppose the spin interaction, your the nucleus is having I is equal to 1. It is not a spin half nucleus. Then according to the splitting pattern will change, because now each of these values, so this is for uh, AXN uh, two equivalent nuclei which are having spin 1 spin. So AXN, where x is the spin, where the spin quantum number is 1, I is equal to 1. If you have having not half, previous example was for half, such as proton, there where the nuclear spin quantum number was half. But if this nuclear spin quantum number is 1, then each of these lines will split into 3. So as I told you, you know this, you have 2i plus 1 values. Why it will split into 3? Because when you have only two orientations are possible for, if I is equal to half, for I is equal to half, only two orientations possible. ms values can be sorry, what I told you earlier, mi is plus half or minus half. But when I is equal to 1, the mi plus 1, 0 or minus 1. So because interaction, so these are three different orientations. Hello. Yeah, disconnected. Okay.